in this part, we are going to look at the sum to infinity of a geometric progression. You've already seen what the sum to infinity of a geometric progression means. Simply put, the point at which all the geometric numbers or the figures within the sequence are deemed to converge. Let's look at these questions. Question 1. Find the sum to infinity of the following. A, 2, half, 8, 1 over 8. B, 2, 0.2, 0.02. So, like the question is asking of you, this is sum to infinity of a geometric progression. We want to know what the sum to infinity of a geometric progression. I think the introductory part just explained what the sum to infinity of a geometric progression means to you. So I'm not sure that we need to talk so much about it. We just want to look at problems that lends or that test that concept of the sum to infinity. And those are something you need to watch out for. Remember that anytime there is a sense that a geometric progression is convergent, when we say convergent, you realize that the terms begin to reduce as you progress from the first term to the second term and the third term. If there is that consistent reduction in the terms, then we say that the series or the geometric sequence is convergent. And you also identify that when your ratio, your common ratio, is always less than 1. Okay, it's almost less than 1. Because remember, the common ratio is kind of reducing the terms successively. So if you are reducing the terms successively, the understanding is that it will get to a point where you can no longer reduce any further. Okay, so we say that your sequence is convergent. At that point, where you put all those items together, we say that you have your sum to infinity. Okay, but if it is not convergent and your common ratio is always bigger than 1, which means that as the geometric sequence progresses, you have the terms in the sequence increasing in number. So how does it converge? Okay, so the problem says that we have two kinds of sequence and we want to find a sum to infinity. Watch out why even the sum to infinity is reasonable in this regard. The first part says that our A, we have 2 plus half plus 1 over 8, and it just goes on. The question says that what is the sum to infinity? Do we even have a sum to infinity in this? Of course. Let's try and find the common ratio. Okay, so the common ratio will be succeeding term minus preceding term. So half divided by 2. Your R will give you 1 over 4. Okay, a quarter. This is less than 1. Is that not the case? Yes, so this is going to give you a convergent sequence. Okay, the sum to infinity, noted by the infinity sign, as was shown in the introductory video, is A over 1 minus R. Okay, so our first term is giving us, we have 2 over 1 minus R, that is 1 over 4, okay? And how do we work that out? 1 minus 1 over 4 will give you 3 over 4. So 2 divided by 3 over 4, we know what to get. That's 2 times 4 over 3. So that's going to give you 8 over 3. Okay, so that's the sum to infinity of this progression. The sum to infinity of this progression, 8 whole number, 8 over 3. That is when we sum this sequence into the future, the approximate value of all those individual terms should be 8 over 3. Okay. The second part said that you have 2, 0.2, then you have 0.02, and it keeps on in that sense. The problem is saying that what is the sum to infinity? Likewise, you divide. Your R should give you 0.2 over 2. What does that give you? 0.2 over 2. So this should give you 2 over 20, and that is 1 over 10, and that is 0.1. It should be easy for us to see. I know you remember that from your basic mathematics, number manipulation. So your common ratio is 0.1, and 0.1 is less than 1. Okay, so if your common ratio is less than 1, like we said, then your sequence is convergent. It will get to a point where it can no longer increase significantly, and hence we can find the sum to infinity. That sum to infinity, S, the infinity sign, again will be 2A over 1 minus r, 0.1. So that's going to give you 2 over 0.9. Okay, so we should be able to work out our sum to infinity for that. You just work that out and get sum to infinity. So guys, that is it for the sum to infinity. The point, the sum of all the individual values if our sequence is convergent. The sum for all the individual values when our common ratio is less than 1. Question 2. The sum to infinity of a geometric sequence is 12. Its common ratio is 3 over 4. Find the first term. This second question on sum to infinity, it plays with a bit of the usual algebra that we know. So it shouldn't be difficult for us to figure it out or work on it. It says that the sum to infinity of a geometric progression is 12. That's what the question was saying. And the common ratio is 3 over 4. Find the first term. Very easy. The sum to infinity of a geometric sequence is 12. So the s to infinity, that's the infinity sign, is 12. If the common ratio is 3 over 4, we just want to find the first term. What do we know for sum to infinity? We know that s is equal to a over 1 minus r. Okay, and we are saying that this is 12. So our a all over 1 minus 3 over 4. What do we get? So 12 is equal to a over. What do we get for 1 minus 3 over 4? Okay, so you're going to have 1 over 4 there, okay? And what is your a? Your a will simply be 12 times 1 over 4. Your first term should give us a nice 3. That's it. That is it. So our first term is equal to 3. That is what we do for the sum to infinity. So in your exam, just look out for that. When you are just giving sum to infinity, do not be confused. It should be easy for us to work it out.